Good morning,
That's
everyone.
perfect. And we hear you well.
Good morning in South Africa. My name is Rutger Marquart. I am a postdoc working with Marcello. And during this presentation, I'd like to give an overview of the work that I started during my PhD and now continue as a postdoc. It's about the integrated dynamics and thermodynamics modeling of sea ice and waves in the Antarctic marginal ice zone. So I'd like to start with some background information. So on the right-hand side, you see a figure which is most likely familiar to you. It's the Antarctic sea ice extent from January to December from a period from 1981 to 2024. The gray thick line is the median extent from 1981 to 2010. After that, you saw an increase followed by a decrease starting in 2017, which even led to a recorded minimum in 2023. And that's basically how it looked like in winter in 2023. And then we see the medium extent in the yellow line from 1981 to 2010. So you see there is quite a significant difference. And the reason for this decline is most likely due to climate change. But how exactly, we don't know yet. And I think that is because the response of Antarctic sea ice to climate change in the marginal ice zone is very complicated. And I think that's the reason why we're all doing research in this field. And in my case, I do sea ice modeling, where our aim is to understand and predict the role of sea ice behavior in the changing polar climates. And due to the decline of sea ice, the impact of waves has become more and more important. And I would like to explain that by making use of figure B. So when the sea ice extent drops, an increasing amount of sunlight radiation is absorbed by the ocean. Consequently, the sea ice cover weakens and becomes more responsive to wind and ocean current forcing. And as a result of that, waves penetrate deeper into the Antarctic marginal ice zone, which hinders the formation of consolidated sea ice, keeping the sea ice cover in a more heterogeneous condition. So basically, the aspect of waves has not really been included in these global climate models. And the reason for that is because these models are obviously less detailed because they are covering a larger distance and they cover a larger time frame. So some parameters in these global climate models are either over or underestimated. And that's basically where I come in, because what I would like to do, or what I'm doing, is I model a smaller domain, and I would like to include aspects that these larger scale models do not include, such as the impact of waves and the heterogeneous sea ice cover. So if you look in figure A, then you see these global climate models. They, for example, make use of averaged values, where I distinguish between two different materials, solid like ice floes and fluid like grease ice, which is just a very viscous material of a very viscous fluid, sorry. Then the idea basically is that figure B is showing a representation of a global climate model. And then I will model a model which is covering a domain size of 5 by 5 kilometers, for example, which then represents one cell in this global climate. And then when we would take the average of my domain, then that could be used as input for these global climate models. So in other words, I'm trying to improve the parameterization of these global climate models. So as I mentioned, I started this work during my PhD, where I developed a two-dimensional dynamics model in the computational fluid dynamics software OpenFOAM, where I distinguish between two materials, the ice floes and grease ice. And in figure A, there is a sea ice layout of one of my simulations, where I show the ice floes in red and the interstitial grease ice in blue. And I model a domain which is more or less 100 by 100 meters squared. It's a two-dimensional model in the XY plane, and it is subjected to a harmonic propagating wave, going in this case from the left-hand side to the right-hand side. And now during my postdoc, I would like to zoom out, or I zoom out and I look at a domain which is 5 by 5 kilometers instead of 100 by 100 meters squared, and I look at a larger time frame. So instead of during my PhD, I looked at simulations which were less than a minute, where now I'm looking at a domain with a time frame of a few days. So the first objective of my postdoc was the upscaling, so from 100 by 100 meters squared to 5 kilometers, and still considering the wave and the heterogeneous sea ice cover, so the ice floes and the grease ice. And because I look at a larger time frame, I now also include the effect. So that is my second objective, to include the thermodynamics in the existing two-dimensional dynamics model in OpenFOAM. So I distinguish between two, because I distinguish between two materials, I also have two different approaches for the thermodynamics. And for the ice flows, I use the one-dimensional thermodynamics model by Tedesco, shown in figure A. And for the grease ice, I use the Fresnel ice production equation by Harpaintner. So first, the one-dimensional thermodynamics model by Tedesco. So she basically considers different snow layers and different ice layers. On the left-hand side, we see the model in the winter condition, and on the right-hand side in figure A, we see the conditions in summer. And as I mentioned, she makes use of different snow layers and different sea ice layers with the heat fluxes coming from the top. And then she basically calculates the thermal equilibrium between the layers, from which she can calculate the difference in temperature and the difference in thickness. And on the right-hand side, I'm using the output from her model is the thickness that I'm using. So that's the one I'm showing on the right-hand side. It's the thickness over the time from January to December. And so in summer, obviously, the snow, because I'm showing you this evolution of the snow thickness and the sea ice thickness. And in summer, obviously, it is 0. And in winter, you can see it's increasing, and then it's going back to 0 again. And I'm obviously not interested in an entire year. I'm also only interested in a few days. So I zoom in on the month of July, where the growth rate is the highest. And then I also include the result from the Fresnel ice production equation that is shown in black. And then what we see is that the growth rate of Fresnel ice is higher than the growth rate of sea ice. And this is something that you will see back in my results that I'll show you a bit later. Then, now that I've introduced both the dynamics model and the thermodynamics model, I'd like to explain how the coupling works between the two models. So in the most simple way, I can basically say that I run the dynamics model in OpenFOAM for one time step. Then I take out the thickness from this dynamics model, and I use it as input in my thermodynamics model. Then I run my thermodynamics model, and I use the output, or run the thermodynamics model for one time step, and I take the thickness and use it as input again in my dynamics model. And then I run the next time step. So that's why it's written in a for loop. But this is a little bit too simplified. So I'd like to go into a little bit more detail. So what we do is we introduce thickness categories to overcome the difference in model dimensions. And what I mean with that is that the dynamics model in OpenFOAM, as I mentioned, is a two-dimensional model in the XY plane. And in OpenFOAM, my entire domain is subdivided by a finite number of control volumes or cells. And the thermodynamics model is a model in the Z direction. It's a one-dimensional model. So ideally, or technically, I could run the thermodynamics model for each cell in the dynamics model. But that obviously is too computationally expensive because I have too many cells. And that's why we decided to introduce thickness categories. So what we basically do is we split up the thickness in the dynamics model up in, let's say, 5 categories. And then we run the thermodynamics model for each category per time step. So if I have 5 categories, then I would run the thermodynamics model 5 times per time step. And then the second complication was the fact of a flow oscillating in a wave, that it is quite a rapid process where it's just moving up and down. And the thermodynamics is a very slow process. And that's what I'm trying to show in figure A, where there's a big jump between capital T1 and capital T2. And there are a lot of oscillations because of the dynamics in between this time step. And now what we are assuming is that we have repeating velocity patterns, which basically means that we disregard the identical wave periods and only simulate one full wave period. So here indicated with a thicker line. So that is that's why I have put these thick red crosses here to basically disregard the identical wave periods. And then it would look like this. Like this. And in this way, we save a lot of simulation time. Okay, now that I've spoken about the method, I'm going into the results. And obviously, we need a configuration for this. And we make use of a SAR image, which is showing the difference in intensity. And that's a SAR image from the Antarctic in figure A. And obviously, a SAR image is showing the difference in intensity, not the difference in ice type. So we had to process this image in order to get an idea of a difference between ice flows and grease ice. So what we did is we have the intensity of the waves in the open water. So we filtered out the waves from this, and then we applied that to this pink box here. And then we assume that the intensity that is left when we have filtered out the waves is the intensity difference from the ice flows and the grease ice, or from the ice type. And then we basically assume that we have only 2 materials, ice flows and grease ice. So that is what we see in figure C. So in this case, then the white are the ice flows and black is the interstitial grease ice. So C is one of the layouts, and then we have figure D, which is just a section out of figure C, which we use a simple, idealized version of figure D we use as a test case also in our simulations. So that's what we get here and on this slide. So on the left-hand side, we see this idealized case, the sectional case. And on the right-hand side, we see the full field case. And what we now would like to do is a sensitivity analysis, where we basically play with the wavelength and different viscosity values. And then I'm talking about the viscosity input parameter values and not the viscosity output. And then we basically run both cases for dynamics only and dynamics and thermodynamics for the different combinations of the wavelength and viscosity. So you can imagine that it's quite a lot of simulations. And unfortunately, I haven't finished the sensitivity analysis yet, but I can show you some preliminary results. So in this case, I'm showing the smallest wavelength with the smallest viscosity input parameter values. And this simulation is the simulation for 48 hours. And on top, I'm showing the dynamics only, and figure B, I'm showing the dynamics and thermodynamics. It's the thickness plot. So this is then the result. That's due to the thermodynamics, there is an increase in thickness. And then in figure C and D, I'm showing the cross-section shown with the black dotted line in figure A and B. And then for figure C, I'm showing the ice flow thickness only. So the grease ice thickness is 0 here to focus only on the ice flows. And then figure D is the grease ice thickness only. Oh, sorry, I mentioned that the black line is the dynamics only, and the red line is the dynamics and thermodynamics. So you do see an increase in thickness due to the thermodynamics, and then this one is for the grease ice. So here the ice flow thickness is 0. And then what we see is that the grease ice thickness increases more than the ice flow thickness, and this is also what we expected from the difference in growth rate, what I spoke about earlier. Then this is a simulation with the full field case, same wave period and same viscosity input parameter values, and also after 48 hours. On the left-hand side, dynamics only, and on the right-hand side, dynamics and thermodynamics. So, and again, you can see there is an increase in thickness. And then next slide, I'm showing the domain averaged values of the sea ice thickness on the left-hand side over time. And obviously, for the dynamics only, the thickness is constant. And when I include the thermodynamics, there's an increase in thickness. So this is for both ice flows and grease ice altogether. And on the right-hand side, I am showing the sea ice viscosity over time. So the domain average sea ice viscosity of both ice flows and grease ice. And then we also see an increase in the viscosity due to the thermodynamics. So that's basically the results that I wanted to show you for now. So I'd like to end with a recap and some future work. So we are trying to get a better understanding of how the thermodynamics impacts the sea ice dynamics by including these details such as the heterogeneous sea ice cover and the wave impact, to eventually improve the parameterization of these global climate models. And for the short-term work is to still get a better understanding of these simulation results, to finish this sensitivity analysis, and to finish drafting the manuscript, which I'm currently working on. Thank you very much. Any questions?
Thank you very much. That was really nice. Any questions from the group? Mike, you have something.
Yeah, I don't want to hog the limelight. Yeah, it's really impressive, and I mean these are really hard problems. I've got a few questions and maybe some comments, but it wasn't entirely clear to me what physics you had in the model. And you talked a lot about the thermodynamics, which I think is what you've added, but the original physics, the flows are able to move with the waves. Is that right? Rutger?
Yes.
Yeah, I
I
mean,
didn't hear
in
your
your
question.
original model,
Yes.
ignoring the thermodynamics, what's the physics in that? Like you've got this open foam, you've obviously got the fluid moving according to Navier-Stokes, and then you've got the ice flows moving according to.
Yes. I didn't want to show any equations in the presentation, but you're right. I've got a momentum equation where I have the drag from the skin drag from the ocean and the sea ice difference. I've got a Krylov force acting at the circumference of the ice flows. And then I've obviously a stress term, which is basically the rheology of the ice flows and the grease ice. Yeah, so that's the momentum.
And these flows can allowed to hit each other, they can collide, or?
Yes, they can. And that works because of the stress difference that comes out is basically from the velocity gradient. So obviously when they collide, there's a difference in velocity, there's strain rate involved. And this from the strain rate, I get a stress.
And then, presumably you can just scale this up. It's just a computing problem if you go to make it bigger. Is that a?
Yes, correct. So the challenge wasn't really to go from 100 by 100 meters to 5 by 5 kilometers. It's more the time that I'm running a simulation. So during my PhD, I was only running less than a minute, where now I'm running for a much longer time window. And that is actually more a challenge than from a smaller domain to a larger domain.
And then, how do you generate the wave? How is that generated?
The wave is just a harmonic propagating wave, which is imposed to the domain. So
as a
it's
boundary
simply,
condition.
yes.
I have a quick question. I think I just didn't understand this, but in that motivation, you mentioned that GCMs have these coarser grids and require some speculative subgrid scale parameterization. And then you use this very fine grid, but one of the main subgrid scale parameterizations in sea ice models is the ice thickness distribution, the use of multiple categories. And you adopted that with about the same number of categories as a typical GCM grid scale, right? Like 5 categories. I didn't.
Yeah, this is an example. The 5 categories. Yeah.
Why I didn't quite understand why you needed the subgrid scale parameterization of the ice thickness distribution. How fine a grid would you need to have to get away with avoiding that parameterization?
So in this case, when I run my simulation of 5 by 5 kilometers, I have like almost 600 by 600 cells. So that is 360,000, 36,000. 36,000 cells. So that's why I don't want to run my thermodynamics model 36,000 times per time step.
Ah,
So when I categorize the thickness and only, let's say I have 5 categories, then I only have to run. So I take the average of each category and use as input in my thermodynamics model.
I understand you now. I misunderstood you. So you're not really using it as a subgrid scale parameterization, but rather that you're running your thermodynamic. I think it's the word categories that threw me off.
Yeah,
But
it's just that the OpenFOAM works with basically subdivides this entire domain in a finite number of control volumes. It's the finite volume method that OpenFOAM uses.
But I follow you now. You're you're actually resolving this in your dynamic model, but you're just running your thermodynamic model less times. So GCM does something very similar with radiation, for example, it's correlated K shortcut. But I got you now.
That seems very sensible to me because you know, it is such a slow process. Like I know myself, we tried to simulate using SPH, which is another sort of method that has pros and cons over OpenFOAM, but it's probably more computational. But we were trying to simulate the melting, but the damn flows didn't melt. You know, it takes so long. So you ended up it was kind of a madness to run the simulation, you know, for 10 years to melt an ice flow. It wasn't going to work. So I think we didn't really think about how to get around that. You know, how to it was obvious now actually, and it's quite interesting when seeing this talk, you know, how the obvious is often missed, but that you've got to run them on different time scales.
Mm-hmm.
Yeah, so if we'd simply simulated, because I'm very disappointed now. I realize how we actually kind of, so I'm wanting to expect them to split up the process, because if we'd done it like that, we could have simulated for, you know, a few periods, worked out how much melting was, or what the dynamics was, and then imagined that continued on without having to simulate every particle of fluid, because that's so costly and it's not essential to the process. Yeah. So that was it's interesting. That's probably that was quite obvious to you, but we sort of missed that.
And I have to say that it's quite a computationally expensive way of doing this, but we still want to figure out the outcome if it's sensible to do it this way. But yeah, we're still working on it. So unfortunately, I cannot draw any conclusions yet from it.
I want to make sure someone else can ask a question, but I just
I'll ask a question.
Yeah, great.
So great talk, thanks. That's really amazing work. I just got confused here at the end because in your results you're comparing essentially the ice growth with dynamics only and dynamics plus thermodynamics. Is that right?
Yes, correct.
I mean, wouldn't it make more sense to compare with thermodynamics only without the dynamics to see what's the effect of the dynamics on the growth? You see what I mean?
Yes. We've been thinking about this, and it's a very good point.
Okay.
So what we are now trying to look at is to run the dynamics only and the thermodynamics only, and then the dynamics and thermodynamics together, and see if there's a difference. That is something that we're currently working on, but like I can't draw any conclusions from that yet, so I haven't shown this now in these slides. But yes, we are actually working on that currently.
Because I imagine one of the main applications here in terms of like large scale modeling would be to understand whether the dynamics really has an effect on the thermodynamics at large scales, right?
Yes.
And if it does, I'll be curious to know what the processes are.
Yes. No, it's perhaps the next presentation.